MATU 206, Week 5, Chapter 4, Parts 1 and 2. In general, if A is a whole number and B is a non-zero whole number, we say that A is divisible by B, or B divides A, if and only if the remainder is 0 when A is divided by B. So we say a number is divisible if the remainder is 0. If A and B are any whole number, then B divides A, written as B divides A, and I always remember it by making the little division box there, if and only if there is a unique whole number Q such that then A will equal to B times Q. If B divided by, or if, I get these backwards, if B divides A, then B is a factor or divisor of A. So this is the divisor, and A is a multiple of B. For any whole numbers A and D, if D divides A and N is any whole number, then D divides N times A. So if we have 5 and divides 10, then 5 will also divide 10 times any other number. For any whole numbers A and D, if D divides A, then and N is any whole number, then D divides N and A. In other words, if D is a factor of A, D is also a factor of any multiple of A. So for example, for any whole numbers A, B, and D where D is not 0, if D divides A and D divides B, then D will divide the sum. So if D is 6 and it divides 12 and 6 divides 18, then 6 will divide the sum of 12 and 18. If D divides A but it does not divide B, then it will not divide the sum. If D divides A and D divides B, then D will divide the difference of that. So if 6 divides 18 and 6 divides 12, then 6 will divide the difference of 18 and 12. But also, if D divides A but it does not divide B, then it won't divide the difference. Divisibility rules. I do spend time with my middle school students to teach them these. It's amazing how often they do come up in the course of our middle school curriculum. So the divisibility rule of 2 is that if the number ends in a 2, or an even number, so if it ends in a 0, 2, 4, 6, or 8, the number is divisible by 2. The divisibility rule for 3 is really fun. What you do is if you have 847, what you do is you add 8 plus 4 plus 7. In this case, that would be 19. And you can even add 1 plus 9, which is 10. And if the sum is divisible by 3, if the sum of the digits is divisible by 3, then the whole number is divisible by 3. In this case, 847 is not divisible by 3. But if we had 681 and we add 6 plus 8 plus 1, we end up with 15, and 1 plus 5 is 6. 6 is divisible by 3, so 681 is divisible by 3. A whole number is divisible by 4 only if the last 2 digits of the number represent a number divisible by 4. So if we have x, y, and z is a 3-digit number, if y and z is divisible by 4, then the whole number is divisible by 4. 5, the divisibility rule for 5, most people know this. If the number ends in 0 or a 5, the whole number is divisible by 5. Divisibility rule for 6 has to be divisible by both 2 and 3. So if you have a number 742, you can check to see if it's divisible by 2. It is, because it ends in an even number. And 3, 7 plus 4 plus 2 is 11, 12, 13, and 1 plus 3 is 4. 4 is not divisible by 3, so therefore 742 is not divisible by 6. They don't list the rule for 7 in the textbook, but it's not that bad. The divisibility rule for 7, if we have a numbers like 917, divisibility rule for 7 says you take the last digit and you double it and subtract it from the rest of the number. So that's 8 and 11 makes 7 and 7. You take the last number and double it and subtract it from the rest, and you get a -7, which, if this answer here, when it gets down to 0 or a single digit, if it's divisible by 7, then the whole number is divisible by 7. Sometimes it's helpful, sometimes it's not. But that is the divisibility rule for 7. Take the last digit, double it, or multiply it by 2, subtract from the rest, and keep going until you get down to a 2-digit or 1-digit number where you can see if 7 divides in evenly. And if it does, it is divisible by 7. If it does not, it's not. A whole number is divisible by 8 if the last 3 digits, so if we have W, X, Y, and Z is our number, if X, Y, and Z is divisible by 8, the whole thing is divisible by 8. But I rarely end up using this rule because I've already picked off the numbers and done what I have to do by using the divisible by 2 rule most often. A whole number is divisible by 9 if the sum of the digits of the whole number is divisible by 9, just like 3, if we have 681, if we add the digits, we get 15. 15 is not divisible by 9, so 681 is not divisible by 9. And whole number is divisible by 10 if the number ends in a 0. The divisibility rule for 2 and 3, 5 gets used a lot, breaking down prime factorization to find common denominators and reducing fractions and things like that. Well worth the time invested to teach it to students and to learn it and use it yourself. The divisibility rule for 4 and 6 and 8 and 10 actually really gets taken up by the divisibility rule for 2. 3, 6, and 9 really gets taken care of by the divisibility rule for 3. The only one that sometimes else comes into play is divisibility rule for 7. So now we have a huge number, 57,729,364,583. Doesn't fit most calculators because most calculators only have 8 digits. Determine whether it's divisible by each of the following. It's divisible by 2? No, because the final digits of 3, it's odd. Is it divisible by 3? Well, that means we have to add 5 and 7 is 12, plus 7 is 19, plus 2 is 21, plus 9 is 30, plus 3 is 33, plus 6 is 39, plus 4 is 43, plus 5 is 48, plus 8 is 56, plus 3 is 59, and then I can add 5 and 9 and get 14 and find out that no, it's because I can also go ahead and do 1 plus 4 is 5. 5 is not divisible by 3, so no. If 2 won't go in, 4 won't go in, 2 and 3 won't go in, so 6 won't go in. It doesn't end in a 0 or 5, so 5 won't go in, and thusly 10 won't go in. If 3 won't fit, 4 won't fit. If 2 won't fit, 8 won't fit. And I don't know if I really want to do this for 7, but let's try. 5, 7, 7, 2, 9, 3, 6, 4, 5, 8, 3. Double 3, subtract from the rest. 2, 5, 4, 6, 3, 9, 2, 7, 7, 5. Double the 2, subtract it from the rest. 1, 4, 6, 3, 9, 2, 7, 7, 5. Double and subtract. 2, 6, 3, 9, 2, 7, 7, 5. Double and subtract. 2, 3, 9, 2, 7, 7, 5. I'm going to run out of room. Double and subtract. So that makes an 8 and a so 9, 8, 2, 7, 7, 5. Double and subtract. Oh, there we go. 18, 0, and 1, 7, 7, 5. Double and subtract is leaves me. I'll write it up here. 5, 7, 7, 1. Double and subtract makes 5, 7, 5. Double and subtract makes 10 and 47. And 47 is not divisible by 7, so this number must be prime. None of these numbers divide in evenly if I did all my math right and applied all my divisibility rules correctly. Prime and composite. So how many ways can we make up an 18? This is an introduction to the concept of prime, where there are exactly two factors, and composite, where there are more than two factors. 18 can be made up in a row of boxes as 1 times 18. It can be made up in 2 rows as 2 times 9. Or it can be made up as 3 times 6. So we also know that 1 times 18 is, product is 18. 2 times 9 is 18. 3 times 6 is 18. 4 times nothing is not a 4 is not a factor of 18. 5 is not a factor of 18, and 6 we're wrapping back around. So we found all the ways we can produce the number of 18 by multiplication. So we can say that 18 has 1, 2, 3, 4, 5, 6 factors. 18 has 6 factors. We can see that 18 is here in this box here as having 6 factors or divisors, because this shows the number of positive divisors that the numbers 1 through 37 have. 1 has exactly 1 divisor. 4, 9, 25 have 3, 6, 8, 10, 14, 15, 21, 22, 26, 27, 33, 34, and 35 have exactly 4 divisors. 16 has 5, 12, 18, 20, 28, and 32 has 6. There are no numbers between 1 and 37 that have exactly 7 divisors. 24 and 30 have 8, and 36 has 9, and I left out 2 because these are special ones. The values that have exactly 2 divisors or 2 factors, this list here, we call those prime numbers. Prime numbers have exactly 2 factors. And they can only be made up of 2 factors. All the other numbers here, other than 1, because 1's neither prime nor composite, are composite numbers made up of more than 2 factors. So a prime number is any positive integer with exactly 2 distinct positive divisors. I've always said that a prime number has exactly 2 factors. Is the definition I've always had. Book obviously looks at it from the divisors category. A composite number is any whole number greater than 1 that has a positive factor other than 1 and itself. So in other words, it's not prime. Are the following numbers prime or composite? Well, if we take 1564 and break it down, prime factorization, we see there's a 2 in it. 2 goes into 15 7 times with 1 left over. That's 8 with none left over, and 2 has another 2 in it. That's 3 with 1 left over, 9 with none left over, and 1. Notice I'm doing short division here from last week. 2 will not go in. Will 3 fit in? 3 plus 9 plus 1? No, 3 won't go in. 4 obviously won't. 5 won't. 7, 391, double and subtract is 7 and 3. And 7 doesn't go into 37 evenly, so no, it won't, and so forth. But right now, we know that it has 1 and 2 and 1564 as factors, so no, it is composite. It has more than just 1 in itself. It has a 2 also. How about 2,781? I wonder if that 2,781, can we break it down? 2 won't go in. Will 3? 2 plus 7 is 9 plus 8. Yes, 3 will fit in. 3 goes into 27, 9. 3 goes into 8 twice with 2 left over. 3 goes into 21 7 times. And so 2,781 has at least a 1, a 3. It may have more in the middle. 2781. It does have more than 2 factors or divisors, so it is not prime either. How about 3 times 5 times 7 times 11 times 13 plus 1? Well, what do we know? Odd number times an odd number is an odd number. An odd number times an odd number is an odd number. So we have odd numbers times odd numbers. We have an odd number, but when we add 1, we get an even number, which means it's divisible by 2. And so this has, for factors, or it has a 1, it has whatever the product and the sum is, and it also has a 2, so that is not prime either. Prime factorization, I do teach this skill to my middle school students. It really, really helps with finding common denominators, and it also helps for reducing fractions. And I've even had students, middle school, 13 and 14-year-old students, tell me, why haven't other teachers taught us this method for working with fractions? Now it makes sense and it's so easy. Finding common denominators by listing multiples, or by the butterfly method of just multiplying each fraction by the other fraction's denominator. While they work, the listing of multiples doesn't really work when you get large numbers. I mean, if you're working with fractions with denominators smaller than 10, okay, listing multiples works. But then when you start getting into algebra, where you can have a denominator like 3x squared y to the fourth, go ahead, list the multiples. It just doesn't work. So listing multiples for finding common denominators doesn't help the student in the future. And if you're doing 2/3 plus 4/5, taking this denominator and multiplying the numerator and denominator by it works, because you end up with 10/15 plus 12/15. That way works to get a common denominator, but it's horrendous when all of a sudden you have 378 as one of your denominators, and 2,394 as your other denominator. And yes, I make students in middle school solve fractions like this, just so they get the practice of working out fractions and not being scared of them. They realize that they actually can do this. So list the multiples of those two denominators, and they're there forever. Multiply by each side by the other denominator, and they get huge numbers. I use prime factorization, and it makes life a whole lot easier. So, composite numbers can be expressed as products of 2 or more whole numbers greater than 1. Each expression of a number as a product of factors is the factorization. And if you work it all the way down so that only prime numbers are left, it is prime factorization. So if we had 378, that denominator I was showing you, I make factor trees, and we'll look at this in a little bit. 2 fits. This is why the divisibility rules are important. 2 goes in because the last digit is even. 2 goes into 3 1 times with 1 left over. 2 goes into 17 8 times with 1 left over. 2 goes into 18 9 times. Now, 2 will not fit, but 1 plus 8 plus 9 is divisible by 3. 3 goes into 18 6 times, and 3 goes into 6 2 times with 1 left over, and 3 and 7. So the prime factorization of 378 is 2 times 3 times 3 times 3 times 7. Some people will write this as 2 times 3 cubed times 7. I generally have my middle school students leave it like that for the purposes of finding common denominators and or reducing the fraction. It's best to have the factors listed out. The fundamental theorem of arithmetic, unique factorization theorem. So it's saying that every composite number can be written as a product of primes in one and only one way, except for the order, and that is the commutative property of multiplication. Says you can order things together, order the products or the factors in any way, and they'll give you the same factor. In other words, 2 times 3 times 7 is the same value as 3 times 7 times 2. It doesn't matter how you order it. That's what this order of the prime factors is referring to. So every composite number can be broken down to a unique prime factorization. That is the fundamental theorem of arithmetic. Prime factorization. To find the prime factorization of a composite number, rewrite the number as the product of two smaller natural numbers. So if I'm going to do this one, I see that a 2 will go in because it's even, so I have a 2, and 2 goes into 8 4 times with nothing left over. 2 goes into 4 2. So now I've rewritten 84 as the factorization or the product of two smaller numbers, and I keep going. 2 is prime, 42 is not, so I have to keep going. 2 is prime, 21 is not, so I have to keep going. And now I'm down to prime factorization. So the prime factorization of 84 is 2 times 2 times 3 times 7. That's what 84 is made up of. I keep going until I get just prime numbers, and that's the prime factorization. So how would I attack 495? 2 doesn't fit. 3 doesn't work. Actually, it does. But I do see that it ends in a 5, so I'm more attracted with the 5. 5 goes into 49 9 times with 4 left over. 5 goes into 45 9 times. 9 goes in 11, and 3 and 3. So the prime factorization of 45 is equal to 3 times 3 times 5 times 11. 260. As I look at it, it's obvious to me, because it ends in 0, that a 10 fits in. So I have 10 times 26. 10 is 2 times 5. 26 is 2 times 13. Those are all prime. So the prime factorization of 260 is 2 times 2 times 5 times 13. Number of divisors. Sometimes we're interested in the quantity of divisors a number might have instead of just the prime factorization. So then you're looking for, what you're looking for then is factor pairs, or the pairs of numbers that multiply. So in this case, 24, the factor pairs are 1 times 24, 2 times 12, 3 times 8, 4 times 6, 5 times nothing, and then we're back to 6. So these are the factor pairs of 24, and so 24 has 8 factors. In algebra, this is a handy tool for factoring polynomials, and another way to think of the number of positive divisors of 24 is to consider the prime factorization. So let's break 24 down in prime factorization. That's 2 times 12, which is 2 times 6, which is 2 times 3. So 24, prime factorization is 2 times 2 times 2 times 3, or as they show here, 2 cubed, because there's 3 of them, times 3. 2 cubed has 4 divisors. 3 has 2 divisors. So what I can say is that there are 4 times 2 equals 8 factors. And I get that by adding 1 to this exponent and adding 1 to that hidden 1 exponent, and the number of exponents of that factor plus 1 times the number of exponents of the value of the exponents times that one equals the number of factors. If P and Q are different primes, M and N are whole numbers, then P to the N times Q to the M has, you take that exponent and add 1, take that exponent and add 1, multiply those together, find the product, and that's how many divisors or how many factors a given number will have. So if we want to find the number of divisors of 1,000,000, we could break it down and say 1 times 1,000,000, or 2 times 500,000. 3 won't fit, or 4 times 250,000, and I could break it on down that way and then count, or I could do a prime factorization. So 1,000,000 breaks down to 1,000 times 1,000, which breaks down to 10 times 100 and 10 times 100, and that's 10 times 10 and 10 times 10, so there are 1, 2, 3, 4, 5, 6 tens. I could have known that just by counting the zeros. So it's 10 to the 6. 10 breaks down to 2 times 5, so, and then I could use the power of a product rule here and distribute that x. So I have, and then I can add 1 there and add 1 there, and I see that 7 times 7 is 49 divisors. And if I want to find the number of divisors of 210 to the 10th power, well, that's 10 plus 1 is 11 is the value I'm going to be working with. But then can I break down 210? I have 21 times 10, which is 3 times 7 and 2 times 5. And so I have 2 to the 10th times 3 to the 10th times 5 to the 10th times 7 to the 10th. But remember, it's adding 1 to each of the exponents. So it's 11 4 times, 1, 2, 3, 4. So that would be 11 times 11 times 11 times 11, which, thank goodness, is there, because I'm not going to do that in my head. 14,641 divisors. That's how we can find out the number of divisors in a given number. Determining if a number is prime. To determine if a number is prime, you must check only divisibility by prime numbers. That's when I was breaking things down. I was checking 2 by 3, by 5, by 7. I'm not checking by 4. I'm not checking by 6. I don't need to check by 8 or 9 or 10, because they're all made up, and we'll find that they'll all fall out because of they're all composite. They're all made up of prime numbers. So we only have to check by prime numbers less than the given number. For example, to determine if 97 is prime, we only have to try to go up until you get to the square root of 97. So we have to try 2. Does 2 fit? No, because it's not. It's not even. Does 3 fit? Will 3 fit in? No, it won't. How about 5? No. How about 7? Double 7, 19 minus 14 gives a negative 5. No, 7 won't. The next one is 11. 11 goes into 97. No, but 11 times 11 is 121, and that's bigger than 97, so I know I can stop. Is 397 composite or prime? 2 won't fit because it's not even. 3, 9, and no, it won't. 19 isn't divisible by 3. 5 won't fit. 397, double 7, get 14. Subtract is a 5 and a 2. 7 won't go into 25, so 7 won't fit. 11, Let's see, 11 goes into 397 three times, 33 and 67. No, 11 won't go. 13 goes into 39 three times, but it won't go into 7. And 13 squared is 169, so we got to keep on going. The next prime number is 17, which 17 squared is 196. Will 17 fit into 379, or 397 rather? 17 twice is 34, with 57, 34. Let's try 3, 21, 2, 3, 51. No, 17 won't fit. 19 squared. 361. No, 19 won't fit either then. So because none of these primes up through 19 and the next prime of 23 squared is bigger than 397, so we don't have to try it. We know that 397 is prime because it's not divisible by any of these prime numbers. Is 91 composite or prime? Well, square root of 91 is less than 10, so we only have to try 2, 3, 5, and 7. 2 won't work because 1 is odd. 9 plus 1 is 10. 3 won't work. It ends in a 1, so 5 won't go in because it's not 0 or 1. And you take 9. You double the 1 and subtract. And 9 minus 2 is 7. 7 is divisible by 7, so 7 will fit into 91. So 91 is composite. The sieve of Eratosthenes. One way to find all the primes less than a given number is to use the sieve or sieve, a sieve of Eratosthenes. If all the natural numbers greater than 1 are considered and the numbers that are not prime are methodically crossed out, the remaining numbers are prime. I've had students do this. I don't see the benefit of it. They really don't learn from it, and maybe after they knew prime numbers a little bit they would, but the way it works is you just cross out 1 because 1 is not prime. You circle 2 and then you cross out all the succeeding multiples of 2. So you're going to cross out that whole column there because it's even. You're going to cross out that whole column, that whole column, that whole column. You're just going to cross out the even columns. You circle 3, the next number, and then you go through and you cross out all of the multiples of 3. So 3, 6 goes, 9 goes, 12 goes, 15 goes. If you've already crossed them out, you can still cross them out. 18, 21, and so forth. Then you have 5. You circle 5 and you cross out all the subsequent multiples of 5. So then that column goes because that's all multiples of 5. The 0 column's already gone. Then you circle 7 and then you cross out 14 and 21 and 28 and 35 and 42. And then 11 is the next number that's not crossed out. You circle it, and you go through and you cross out 22 and 33 and 44 and 55, 66, 77, 88, 99. And then you would circle 13. And you go through and circle the next number and then cross out all its multiples until finally you get up and everything's either circled or crossed out. The circled numbers are the prime numbers, and the crossed out numbers are not. I tend to try and have my students memorize the first 10 prime numbers, or 2, 3, 5, 7, 11, 13, 17, 19, 23. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 29. That generally gets us through because that helps us work with numbers up to about 900, because 30 squared is 900. So when we're working with numbers less than 900, the first 10 prime numbers really help us working with common denominators, reducing fractions, and various other things. The greatest common divisor is the greatest common factor of two whole numbers, a and b. So it's the biggest number that will divide evenly into two numbers. So if we have an example, two bands are combined to march in a parade, a 24-member band will march behind a 30-member band, and the combined bands must have the same number of columns. We're looking for what number will divide into both of these evenly. Um, I would tend to find it by prime factorization, so I have 2 and 12, 2 and 6, 2 and 3. 24 is made up of a 2, 2, 2, and a 3. 30 breakdown is 2 and 10, 2 and 2 and 15, which makes 3 and 5. And so a 30 is made up of a 2, a 3, and a 5. And then to find the greatest common divisor, I'm looking for the numbers that are the same on both lists. And so there's a 2 and a 3 on both lists, so I multiply those, and there's my greatest common divisor. So the greatest common divisor of 108 and 72, I'm going to prime factor. 2 goes in there 54. 2 goes in there 2 times with 1 left over, and 7. And then I have 3 and 9 and 3 and 3. So 108 is made up of a 2, a 2, a 3, a 3, and a 3. 72 will make up with 8 times 9, which is 2 times 4, and 2 times 2, and 3 times 3. So 72 is a 2, a 2, a 2, a 3, and a 3. There's a 2 on both lists, another 2 on both lists, a 3 on both lists, and a 3 on both lists. So the greatest common divisor is 2 times 2 times 3 times 3, or 4 times 9, which is 36. So 36 is the greatest common divisor. It's the largest number that will go in both 108 and 72. The greatest common divisor of 0 in any number is just the number 0 divided by 13 is 0. It does go. The greatest common divisor, remember, we're looking for things that are common. So if there's a 2 and a 2 cubed, well, there's 1 2. There are 7s on both, but there are 2 of them here, and so there are times 7 squared. There's no 11, there is 113, and there's no 17, so the greatest common divisor of 2 cubed times 7 squared times 11 times 13, and 2 times 7 cubed times 13 times 7 is 2 times 7 squared times 13. And this way we can find greatest common divisors of 3 values also. X equals 2 cubed times 7 squared times 11 times 13. Y equals 2 times 7 cubed times 13 times 7. And Z equals 2 squared times 7. I see there are 2's. There's a 2 cubed, a 2, and a 2 squared, but there's only one 2 that's on all 3. There's a 7 squared, a 7 cubed, and a 7, so there's a 7. I'm out of digits here, so the greatest common denominator of this mess is 2 times 7, or 14. The Euclidean algorithm method. If a and b are any whole numbers greater than 0 and a is larger than or equal to b, then the greatest common divisor of a and b is the greatest common divisor of the r, the remainder, and b, where r is the remainder when a is divided by b. So you're going to divide a by b and keep going, and whatever the remainder is the greatest common divisor. So it's a lot of division. You have 2 positive numbers, you divide the larger number by the smaller. If the remainder is 0, then the last divisor is the greatest common divisor. If not, you just keep dividing. So here's an example. If we have 10,764, 2,300, I would tend to prime factor them and look for the numbers that are the same. But here we are dividing 10,764 by 2,300. We see that it goes in 4 times. 4 times that is 9,200, with that as the leftover remainder, which now becomes the divisor here. And this number is the dividend, goes in to be divided. 1,564 will go into 2,300 once. And So we do that again. We take, after the subtraction, we take that there and we take in there and we divide. There's 2. So 2 times 736 is 1472. You do the subtraction, you get 92. Put it there. 736 is goes there, divided in 8, and we get a remainder of 0. So the greatest common divisor is 92. That's the largest number that will divide into both 10,764 and 2,300 evenly. Shifting least common multiple, if you're listing multiples of, say, like 2 and 7, 2, 4, 6, 8, the multiples of 2 are the even numbers. The multiples of 7 are touchdowns with the extra point. And you're looking for the least one, the smallest one that's the same on both lists, and we bump into 14 right there. This is a common method for teaching students how to find a common denominator in order to add and subtract fractions, which is really great when you're working with small numbers, like I said earlier. But if you're working with larger numbers, if you have 3 over 117 plus 87 294ths, it's really not fun listing the multiples looking for the smallest one. So anyway, we'll go ahead, and hot dog buns are usually sold as 10 to a package, or hot dogs, and the buns are sold 8 to a package. And so how can you get a combination of this such that you have an equal number of hot dogs and buns? So you can list the multiples: 10, 20, 30, 40, 50, 60. You can list the multiples 8, 16, 24, 32, 40. I see that 40 is the least common multiple, so we would need to order 4 bags or 4 packages of hot dogs and 5 packages of buns in order to get equal numbers. The least common multiple of 2 non-zero whole numbers, A and B, is the least non-zero whole number that is simultaneously a multiple of A and a multiple of B. So I would use prime factorization for this also, but let's look at the number line method. This method is useful for helping students understand what you're talking about when you're talking about least common multiple. So the least common multiple of 3s and 4s, you show them, well, there's a 3, there's another 3, there's another 3, another 3, another 3, and so forth. And you can say there's a 4, there's a 4, there's a 4, there's a 4. This is the first place where both a 3 and a 4, so 12 is the least common multiple of 3 and 4. I do like this as an introductory method to least common multiple. Although with my middle school students, I never use the term greatest common divisor and least common multiple. I've found that they really don't have much meaning to the students, and it just leads to confusion, but that's just me. I would use the prime factorization method to find this. So when you break numbers down, then you're looking for the largest one that's in them. So if you have 2,520, when you break it down, you get 2 cubed times 3 squared times 5 times 7. When you break 10,530 down, you get 2 times 3 to the 4th times 5 times 13. This time I'm going to take the 2 cubed. I see there's a 3 squared and a 3 to the 4th. I'm going to take 3 to the 4th. I see there's 1 5, so I'm going to take it. There's 1 7, I'm going to take it. And there's 1 13, I'm going to take it. When I multiply all those together and get 294,840, I know that that's my least common multiple. How do I use this with fractions? If I have 2 ninths plus 7/15. How would I use this? Many people would just go 9, 18, 27, and so forth. I'm going to break 9 down to 3 times 3. So 9 is made up of a 3 and a 3. 15 breaks down to 3 times 5. So 15 is made up of a 3 and a 5. Then I say, what's missing? There's a 5 missing from the fraction with the 9 in the denominator. There's a 3 missing from the fraction with the 15 in the denominator. So I'm going to multiply the 2/9 times 5/5. I'm going to multiply the 7/15 by 3/3, which gives me 10/45 plus 21/45. I now have my common denominator, which I can just carry through as 45, and I can add my numerators, and I get 31/45. I can try reducing them. I do know that the prime factorization of 45 I already have as 3 times 3 times 5. That's what I have here. And then I can just do 31. Will 2 go in? No. Will 3 fit in? 3 plus 1 is 4? No. Will 5 go in? Doesn't end in 0 or 5, so no. Will 7 go in? Double the 1, subtract 3 minus 2 is 1. 7 won't go in. And I know that 7 squared equals 49, which is larger than 31, so I know that 31 is prime, and I'm done. There is my fraction, and I know it is with absolute certainty that it is reduced, and it wasn't all that hard. That's what I do to teach my middle school students to find a common denominator for adding and subtracting fractions. And most of them, by the time they leave my classroom, fractions are no longer a mystery. They're no longer scary. They're just something that just shows up in math every once in a while that you just have to deal with.